Okay, guys. On your desk, you should have notes. Guys, you should be in your seats, ready to go. This is a topic that we're starting today that is usually on the AP exam as one of the free response questions. And you're given an accumulation function and usually a graph of the derivative. So we need to review a couple. What I like about this unit is it ties together lots of different concepts. I think you're going to like it too, right? All right, let's see. Okay, let's say that you're given f of x, capital F of x, is equal to the definite integral from 3 to x of f of t dt. First thing I want you guys to do is get the derivative of it. Remember that second FTC, how you find the derivative of an accumulation function. And by the way, for people that weren't here for the test on Friday, we reviewed on Thursday, so you probably want to watch the video for that. We just went through the practice exam that it was based upon, and we went through and kind of reviewed some of the important ones there. So. I think I have like 20 people that have to make that up, 21 people. So we need to get going on that. Alright, so first things. Anyone want to say what the derivative, capital F? Yeah. So wait, what is it going to be? Yeah, because it's derivative of upper 1 times plug in upper f of x. But derivative of lower is 0, so you just get f of x. Good. That's from when we did the second FTC. Does that sound familiar? Okay. Now what I want you to do is identify one point on the graph of capital F. Okay, so there's a function, capital F of x. I want to know if there's one point on that graph that you know. This is how it's defined. Think of one value of x. If you plugged it in, you would know what you get. Any number you could put in there and you would know the outcome. Everybody's got their hand up. I just don't know what to pick. What? You see it. Say it, Ellie. 3. And what is f of 3? It's 0. So there is a point on the graph of f that we know. It's the point 3, 0. Right? The definite integral from 3 to 3, I don't care what it's of, is always going to be 0. Now, what does the definite integral of lowercase f, which you recall is the derivative of uppercase, what does the definite integral of the derivative from 3 to 8 represent? It's a difference in something. In what? Well, how would you... Not x's and y's. If I... The y's. It's a difference in the y's. Because if you were to actually evaluate the definite integral, what's the first thing you would do? Antiderivative, right? Which is capital F. And then what would you plug in? The A. So you would get f of 8 minus f of 3. You're just getting the change in the original function, the change in the y coordinates on the original function. Call that the net change. So the net change, or in f, or you can just call it delta f. You're getting f of 8 minus f of 3. That's such an important concept, this unit. Well, always. That when you integrate the derivative, yes? Want me to read what that says? That's capital F of 8 minus capital F of 3. And a change in f. What it gives you is the change. She lost her glasses. Yeah. Now, how would you find f of 8 given the graph of lowercase f? In other words, if you're asked to find f of 8, first of all, let's see how it's defined. Then we'll talk about what we do if we're just given the graph. Yes. Yes. Better? Okay. F of 8 would be defined as the definite integral from 3 to 8 of f of t. Now let's say we're not given what f of t equals. We're given a graph of f of t. And let me just make something up here so you can... Let's say we have a graph. I just don't know what to make it look like. Let's just make it look like the line. Oh, I gotta go all the way out to 8. Right. 1, 2, 3, 4, 5, 6, 8. And let's keep it nice and simple. Let's say it's... We'll have it alternate between -3 and 3. Let's say it's y equals 3 all the way up until 5. And then it goes down to the point 6, -3. It's a nice line. Oh, I kind of missed that. Should have hit the 5. There we go. And then it goes over. All right. What did I say? What did I say? It goes over to 4? Over to 5? Oh, no wonder I made it. That's not good. All right. Well, then it kind of hits it in the half. This one. It's not. I should have stayed with the integers. All right. Let me just highlight that. So that's the point 6, -3, and this is the point 5, 3. All right. So we just have a graph of f, lowercase f. And we want to evaluate the definite integral from 3 to 8. How can you use the graph of a function to evaluate the definite integral of a function? Antiderivative. See, with the derivative, then I could just get the slope, and that would be great. The definite integral of a function, when you have a graph of the function, it has nothing to do with slope. To do with. Yes. Okay, that's going to have to be a big thing. Okay, where it crosses. Actually, mine crosses at like 5.5. But it actually has to do with area. Is the definite integral always just equal to the area? Like, would it just equal... Between 3 and 8, what do we do with the areas? You've seen it. Sing it, Jessica. Area above minus area below. That's what the definite integral gives you. So if you're able to calculate the area above minus the area below between those limits of integration, you've got the value of the definite integral. I'm so sorry I made this so ugly. I was really trying to keep it very simple. I don't know what happened here. Oh well. Well. just didn't work out. Alright, let's figure out between 3 and 8 the total area above. Well, I'll do this rectangle here. No, I'll let you do that. Alright, so from 3 to 5, that's a rectangle. What's that area? So that's 6. This is the one that's going to be annoying in there. What's the area of that little triangle? Because it's 1/2 base, which is a half, times height. 1/2 base. 1/2 times a half, that's a fourth, times 3. 3/4 it should be. So 0.75, that's what you said? Sorry. This is supposed to cross at 5.5. So it's not good. I'm going to tell you right now, it's not good. Bad. Alright, what about the area of this triangle? Same thing. It's 1/2 base, which is supposed to be a half times height. 0.75. Okay, we're home free now. And then what's the area of this rectangle down here? 6. 0? Yeah, it is 0. It kind of worked out nicely in the end. So the area above is 6.75 minus the area below, which is also 6.75, equals 0. These are kind of all the things we're going to have to be able to do with these AP problems. There's a lot of prep work today, getting you ready for it, but trust me, it's going to be worth it. Once we start and we get going on, you're like, oh, this was worth it. All right. Down there. Oh, you know what I got to go over? Because I know it was confusing. Yeah, I'm letting it change. I'm just going to... Okay, so what I want to do, guys, is go over a few of these. All right, so you understand. So I'd like you to take your questions. Can you be more specific? Because it's hard to just do. Like with the graphs. Okay, let's talk about like number 6. That's not what I want. This thing. Okay, in question number 6, you're given a graph, the rate of flow measuring gallons per hour. Say gallons per hour. On the y-axis and hours on the x-axis. And I give you a little graph. So they've given you a graph of the derivative. I know it's a derivative because the units are gallons per hour. And they want you to get the total amount of water, total number of gallons that flow over the 24-hour period. Okay. So it would be the definite integral of this rate to get the total amount. So the total amount of water that flows would be the definite integral from 0 to 24 of this function. Now, I don't even think they named it. I'll just call it g of t. So I'm going to have to get the value, bless you. And guys, remember, when you have a definite integral, the units you get by, what do you do with the units of g of t and dt? Do you remember? Get the units, you multiply. So if you multiply the units gallons per hour times hours, it's going to give you the total number of gallons. Right? So the thing is, we can't just take the definite integral. We're going to have to get it from the graph. And so to get the value of the definite integral from the graph, area above minus area below. Well, it's all area above, so I just got to figure out what this area is. So to do this kind of a problem, you're going to need to know what the area of a single box is. So just look at one little box there. What does it represent? How much water? What's the 1,200 gallons, right? Because it's 200 gallons per hour times 6 hours would be 1,200 gallons. So every box is going to represent 1,200 gallons. And we want to know the total area, what that represents. So let's figure out about how many boxes there are under this curve. You're going to have to... Well, full boxes, how many do you have of those? 7. Okay, then you got these pieces. So if you had to judge it closer to 8 or 9. Alright, but we're not looking. Let's say 9. Okay, and then we'll check. So we know technically it's a little less than 9, but we're gonna use 9. So 9 times, remember each box represents 1,200 gallons. Alright, there are 9 boxes. What do you get? 9 times 1,200. 10,800. And that's there, so that's good. We said approximately. Was that? You don't like this approximately, do you? I know. So yeah, but I like going over these because it just, those especially, because it really just, the years, okay. You want to do one with the years? Yes. Yeah, like number 9. Uh-huh. The population. Yeah, if they don't give you a different starting time, take the time they give you as a starting time. Like that's t equals 0, 1950. Yeah, yeah. And so if you integrate, and you don't use the actual years for the time, you use like 0 to 30 for that. Yeah, and that's actually a derivative because you see how the units are in thousands per year or whatever? That's the change in people per year. So that's what you want to integrate to get the change, the total change in the population. But you do have to add that to the original value. So in number 9, you want to figure out the population in 1980. That's when t equals 30. So you're trying to find the population at time 30. You're going to use the population that they gave you in 1950. We'll call that P0, which is 120,000. And we're going to add to that the change in the population. And the way you get the change in anything is take the definite integral of its derivative. So you're going to want to integrate its derivative. Now the thing is with this, just got to be careful of the units. If I just integrate the derivative and I get 7, it really means 7,000 because it says measured in thousands each. So it's really 1,000 times this, which I'm just going to pull out front 1,000. 0.01. But if you take the definite integral of the derivative from, let's talk about the limits of integration. What would they be? You want p of 30, you're going to take p of 0 and add the change from what time? 0 to 30. Well, it's just because they said that this rate of change measures is measured in thousands of people per year. Okay, that's why I had to throw that in there. Normally you don't have that. Or if you want to avoid that, you could have just figured out how many thousand you'd have by just putting 120 plus the integral of that. I just know your answer altogether is thousands. And then you could pop that in your calculator if you want. Get that. Or take the antiderivative and do it yourself. Right, but this is the key thing here. When you integrate a derivative, you get the change, in this case, in the population. You integrate the derivative of the population. Are there other ones you would... What's that? Are you getting it? You're not getting it? Seriously? Can I see your calculator? Oh. Oh, so you took the antiderivative. For this part? Okay. And then 360... And then you added it to the 120 or no? Oh, that's why. Yeah, because remember, if you integrate the derivative, you're just getting the change in the y. So you got to actually add it to the original value. Yeah. Plus 360,000. And then it should be 40,000. But that's... Yeah. Yes. All right. But that's really what I wanted you to get out of that day, was that, you can get a change in a quantity by integrating, take the definite integral of the derivative, and if you're not given a function to actually integrate, you can get it from the graph. And that's what we're going to be using here today. So I guess we'll just get back to that stuff. Oh, let's see what you remember. What happened to my thing? Way back when, well, no, let's not say, no negative comments. Guys, with this type of question, you're basically going to be given the graph of a derivative, and you're going to be asked questions about the function. So it's so important that you know the connection, the relationship between the two. Like if you know the derivative of a function is negative, what's the function doing? Decreasing, because the slope of the tangent lines are all negative. All right, that means the function function is decreasing. This little chart is real important. If you know the derivative is positive, what do you know about the function? It's increasing. Now with the derivative, the slopes of the tangents are changing from negative to positive. Yes, it's a min, relative min. From negative to positive, make sure you're reading left to right. That's what we read in this country. If the slopes, the derivative is changing from positive to negative, what about the function? Next. Now we got one thinker. If the derivative, the slopes are increasing, left to right, the derivative is increasing, what about the function? Maybe. Well, if the first derivative is increasing, what about the second derivative? Yeah, it's positive. If a first, see, that's the kind of connections. So if the first derivative is increasing its derivative, the second derivative would have to be positive. And if the second derivative is positive, the function is concave up. The slopes are increasing as you go left to right. So yeah, the function has to be concave up. If the slopes, the derivative is decreasing, so the slopes are decreasing as you move left to right, what about the function? Concave down. Now, what if the first derivative has a relative max or min? Function has a point of inflection, because that must mean that the second derivative is changing time, right? So the original function is a point of inflection. So we got to be solid on all these, because we're going to look at graphs of derivatives, and they're going to ask us about the function, and we got to know this. We got this. I know you're dying to get to it, and I'm only going to be able to start it a little, because I have to cover all this stuff before. It's going to be worth it. It's going to be so worth it. Alright, this part I'm going to skip, but just a couple more things, kids, and then bear with me, we got it. Okay. So, you're going to be given an accumulation function. Some function that's a definite integral of some other function. The first thing, and no one's going to tell you to do this, you're going to have a little voice in your head that's going to say, take its derivative. Right? And that's what you're going to do. When you see one of these, what is the derivative of the definite integral from c to x of f of t dt? It's just going to be f of x, right? Yes, because when you take derivative of lower, that's 0, so you won't have that. Okay. The reason you're going to do that is because they're going to tell you, oh yeah, this is a graph of lowercase f. But you're going to say, oh, but that's just the derivative. That's equivalent. I can't reach. Sorry. That's the equivalent of the derivative of the accumulation function. I'm looking at a graph of the derivative of my accumulation function. Now, when will an accumulation function have an x-intercept? Okay, when it crosses the x-axis, but I can't see it. I can't see my accumulation function, which is its derivative. Look how it's defined. When will it have an x-intercept? Give me one value of x. When it's c, right? When x equals c, what is f of c always going to equal? 0. Just put this over. So, it will always, when I say when does it have an x-intercept, I mean when does it equal 0? It will always equal 0 when the upper limit equals the lower limit. So there's one point on the graph of this accumulation function that I know, right there. Do you think that it's going to be 0 any other places? Anywhere else? You do? For the max? Oh, actually, because if I go out to where this max is here, it would be the definite integral. Let's say I'm going to call it z for 0. If I took the definite integral from c to z, remember definite integral, area above minus area below? What would it equal? 0. So that's going to be a 0. And do you see anywhere else where it would be? Yeah, over here. That would be 0. So we have 3 points on the graph of this accumulation function. Now we know. So, I should clear this out. So it's going to equal 0 at any other value z such that the area above the x-axis equals the area below between that number and c. Now, how does changing the value of the lower limit of integration affect the graph? Does anyone remember? I think we saw like once really quick. Like if instead of taking a definite integral from 1 to x, we took it from 2 to x. I'm going to tell you, but I want you to like understand it. There's no way I can like go underneath. I don't think. Can I scroll this? Oh wait. Oh yeah. No, I'm not going to tell you. Okay. Here are 2 functions. They're both defined as definite integrals, right? This one's from 0 to x of 2t, and that one's from 1 to x of 2t. Yeah. Okay. So, yes. So how would their graphs be different? First of all, would they have the same derivative or different derivatives? Same derivative. They both have a derivative equal to 2x, so they both have the exact same shape. But if I actually figured out what f of x was equal to, I would take the ni derivative, and this is what you were saying there, Gina. I'd plug in the upper, the lower, and subtract. So f of x is just equal to x squared. What's g of x going to be? Yeah, g of x is going to equal x squared minus 1. And what type of translation? They only differ by a vertical shift. Don't answer me. Yeah, that's the only thing. So I know these are weird functions because you don't really get to see what they are, but just realize if you have 2 different accumulation functions, the only thing that's different is the lower limit of integration. They only differ by a constant. All right, now comes the fun part, I think. Oh, one other thing, but I think you're good with this now. So we said if you integrate the derivative of a function, you get the net change, the total change in that function. And if you're not given f of t, so you can't actually take the antiderivative to get the definite integral, you're going to have to know how to get a definite integral using the area. So it's area above the x-axis minus the area below between a and b. And by the way, if you're going to get the definite integral from the area, the lower limit has to be less than the upper limit. So a has to be less than z. If not, you switch them and the whole thing's the opposite. It's not a big deal. Now we're finally ready to have fun. Let's do this. Oh, by the way, I've included what I call an accumulation function. I wrote down every single thing they could ever ask you about accumulation functions, like what to do. It's exciting. It's March. Okay. March 17th. Okay. We are going to answer so many questions about this one function. This is our gigantic problem. A real AP free response question on this would have maybe A through C, A through D. It's got to have A through M. I've tried to put every question you can ask, but yeah, I know. Now, g of x is defined to be the definite integral from negative 3 to x of f of t. Okay? And this is the graph of f. What should you be thinking when you see this? It's its derivative. And what is g prime of x? F of x. So when they say to you, hey kids, here's a graph of lowercase f, you know it's really a graph of g prime, right? That's equivalent to g prime. So you're looking at a graph with a derivative. First thing they ask us is, what is g of 0? This is g prime. If you want to get values of g, you're going to have to use this definition. So g of 0 equals what? Definite integral from negative 3 to 0 of f of t dt. We're just popping in the 0 for the x, right? Oh no, they didn't tell me what f is. They only gave me a graph of it. How do you get the value of a definite integral from the graph? Area above minus area below. So I got to look at this graph between negative 3 and 0. Negative 3 here and 0. Oh, it's all above. So I'm just got to get the area of that. How are we going to get that area? What shape is it? Trapezoid. Now, area of a triangle is 1/2 base times height. What's the area of a trapezoid? 1/2. How many bases is it? 2. So it's 1/2 the sum of the bases times the height. All right. So we're gonna. It's 1/2 the sum of the bases times the height. Now the bases are the parallel sides. So 1/2. What's the length of this base over here? Nope. 2 plus what's the length of the other base? 1. So it's 1/2 the sum of the bases times the height. The height is the distance between the bases. 3. Okay. So it's 1/2 3 times 3. G of 0 equals, what does that equal? 4.5. Okay, I'll keep this. So that's annoying. You have these areas because it's a definite integral. You're going to like the next one though. What's g prime of negative 3? 2. Oh, because I said you like it, you just picked a number you'd like? Yeah, this is a graph of g prime, right? Remember, f is the same as g prime. So if I say what's g prime of negative 3, you're looking at a graph. On what intervals is g increasing? So when g prime is positive, that's what we're looking for. So just I'm going to put that there. So negative 4 to 3. I like that. It's okay that it's 0 at 1. I mean, some people like to break it up at there, but you're not going to lose any points for that. See, from negative 4 all the way up to 3, it's the graph of g prime is above the x-axis. It's positive. Okay. On what intervals is g decreasing? So negative 5, I'm actually going to include it because it's negative there. So negative 5 to negative 4. It's 0 there, so maybe I won't include it. You're not going to lose points for including the endpoints. And then anywhere else? 3 to 4. And I'm definitely going to include the 4 because it's definitely negative there. Where it's 0, you don't have to include it. You can or you don't have to. Alright, so your homework, it's problems 2 and 3 from this packet. So first thing you should always do is figure out what the derivative of your accumulation function is. So you see that. Let's see what you can do with these. We're going to finish the giant problem tomorrow. Yay. Yeah, and don't forget to use the guide if you get stuck.